Thank you very much. Good morning, everybody. Thank you, Banky. So I'm here to tell you a little bit about some of the problems that myself and my students have been thinking about for the last couple of years or so when it has to do with estimating and controlling for fairness in machine learning predictors. So it does not.
They don't see the good output. They see this presentation. So.
Okay, here we go. All right, so I don't think I need to really convince you hard to tell you that oftentimes when machine learning algorithms are deployed in the wild, they tend to inherit biases that are already present in society, and these can be very problematic in healthcare and other domains as well. And of course, this is to the extent that there are many guidelines and upcoming regulations that basically encourage us to think about these problems from the ground up. Now, when we talk about fairness in the context of machine learning, we basically need to settle on what we mean when we say fairness or unfairness, and there is a variety of different definitions that we can take. I don't want to spend time on this because time is limited, so instead I'm just going to focus on these notions of associative fairness or group fairness, and these are notions that basically measure different rates of accuracy among different demographic groups. So we will need just a little bit of technical details. So I will be using features in some vector space, in some RD, in some D dimensions. We will have protected or sensitive attributes. You can think of these labels as determining something that you want to control for, such as biological sex or race or any other demographics. Here we're just assuming that they are binary for simplicity. They need not be. And the response that we want to predict, Y also here assumed binary for simplicity. So with these notions, you can go, and most of the people in this room would go and train a predictor with a function f that gives you a predicted response. And so this notion of fairness, of equal opportunity, what it measures is the true positivity rate among two different groups. So you would go and measure the positivity rate for the group A equal to 0, and you would measure the true positive rate of the group A equal to 1, and you would require these to be the same. And if this is met, you would say, according to this definition, that your algorithm is fair. Okay, now, in order, if you want to estimate these things, these true positivity rates per group, you need samples from the entire joint distribution. You need samples from the features, the response, and the sensitive attributes that you're trying to control for. And that seems obvious, but that is actually a problem. Here is a little quote from Brian Christian's book, The Alignment Problem. I'll just read it out for you. One engineer that I spoke with complained that his management repeatedly stressed the importance of making sure that the models aren't skewed by sensitive attributes like gender and race, but his company's privacy policy prevented him and the others from accessing the protected attributes of the records that they're working with. So in the end of the day, they have no idea if the models are biased or not. Omitting the protected attributes makes it impossible not only to measure the bias, but also to mitigate it. And you might seem that this is anecdotal evidence, but this is actually quite ubiquitous, and it happens all the time, particularly in medical imaging. This is a snippet of the RSNA, the Radiology Society of North America Pneumonia Detection Challenge in Kaggle, which is a coding competition. They put together a very large data set of chest x-rays that has been thoroughly annotated by radiologists. But these doesn't record race, or it doesn't even record biological sex of the scans. So it prevents us from measuring the degree of bias that our machine learning models have, and of course, correcting for them. So that's the question that we wanted to solve. So we're going to do that in the following manner. We have a data set 1 that only observes features and responses. We don't have access to the sensitive attribute like I just described. And with this, we can train a predictor for our for our response y hat. We're going to assume, however, that we have access to a second data set over features and protective attributes so that we can train a predictor a hat for the sensitive attribute. So we're going to be predicting the sensitive attribute that we cannot observe. Now, this sounds a little bit crazy when it was first suggested to me by a friend who's a radiologist, but I promise that this will make sense. With these things, you can actually regard these two notions. This is the TPR. This is nothing different from what I already showed you. This is the true positive rate for group A. This you cannot compute because we don't have access. We don't see who's male and who's female in our data set. However, we can compute this estimated TPR where we simply impute the sensitive attribute that would predict instead of the ground truth. And of course, we're not assuming that this sensitive attribute predictor is perfect. There will be an error here. And so the question is, how can we use these estimated TPRs to precisely control the difference in the true TPRs? So that's what I'm going to show you. The result comes in the form of a formal mathematical statement. It comes in the form of a theorem. And don't worry about the specifics of this. What you should keep in mind is that what we are saying, what we can show, is that the true difference in TPR, the disparity between males and females, for example, that you cannot compute, can be upper bounded by the maximum of two quantities. And these quantities are linear functions of the estimated TPRs that you can compute. And so on the one hand, it's good to know that these bounds are tight. In other words, there exist distributions of data where this upper bound is actually met as an equality. But more importantly, what this is telling us is that we are bounding, we are giving you a certificate of how large the true TPR that you cannot compute is based on quantities that you can compute in this incomplete data setting. So now going back to the example and to just illustrate how this works, you go back to this pneumonia detection challenge, and anyone can go and train a machine learning algorithm to predict the presence or absence of pneumonia. And you can do this pretty accurately. In this case, you have a predictor, an accuracy of about 95%. But then the question is, if a regulatory agent comes and says, well, your algorithm seems quite accurate, but do you have a maximum difference in TPR of at most, for example, 6%? In principle, you couldn't answer that question. Now we can answer that question because I can give you this upper bound. So what you're seeing here on this graph, on the y-axis, you have this fairness violation, which literally is the difference in true positive rates. In red, you have the true TPR disparity that you cannot compute. Here we're computing it because we have access to some other data, but this quantity you should not be able to compute. What we can tell you is we can certify that the true positive rate disparity is not going to be above 10%, even though we don't know, we don't have access to the ground truth sensitive attributes. And in fact, you can do more than this. I haven't told you how, but you can actually not just estimate, but also correct for these true positive rate disparities. So if 10% is too large, that's okay. Maybe we need 6%. And so we can reduce the difference in TPR rates, even without having access to the ground truth information of, for example, who's male and who's female. This is joint work by my PhD student, Bipul Bharti, and my friend and collaborator, Paul Yi, who's a radiologist at St. Jude Hospital. Thank you very much.